going to prove that the square root function is continuous wherever it's defined. And if you look at the graph of the square root function, you'll notice that 0 is kind of a special point because it just ends abruptly, but all the other points will be roughly the same. So we have two cases. So one is if c equals 0, then what we need to prove is we need to prove that f of x minus f of 0 less than epsilon if x minus 0 is less than delta. Right, and I get to pick the delta. Well, this boils down to square root of x has to be less than epsilon. In other words, I need x to be less than epsilon squared. So, bring this over here. Notice I can let delta equal epsilon squared, and then I get 0 is less than x minus 0, which of course this is just equal x because the domain is positive. So, is less than delta equal to epsilon squared. So that's the basic idea for the proof that's continuous at 0. But now we'll prove the case where c is not equal to 0, which is a little bit harder. So again, I start with what I need. How will I know when I'm done? Well, I need f of x minus f of c has to be less than epsilon. Well, let's figure out what this is. F of x minus f of c. Oh, that's just equal to the square root of x minus square root of c, absolute values. Well, what do I know? I get to assume that x minus c is less than delta, so I get to pick what the delta is eventually. How should I pick it? Well, the thing is I need to incorporate this x minus c in here someplace. And the usual trick, right, I'm just going to multiply by 1. Right, I know my algebra well, so I know if I multiply by this 1, good things will happen. And let's just make this absolute values. Notice, if I FOIL here, I get square root of x times square root of x, just gives me x. Square root of x times square root of c gives me positive square root of xc minus square root of xc. They cancel it, and I get minus square root of c squared, which is just c. And then in the bottom, I get this thing. Okay, so that's good, because now I have this in here, which I can control. But the problem is I don't know what this x is doing in the denominator. The c is fine, it's a constant. Well, let's see. I can always go bigger. So I can make this entire thing bigger by making the denominator smaller, which means I can just drop off this positive term. Right? This is going to be less than or equal to x minus c over square root of c. So I need this less than epsilon. So I need x minus c has to be less than epsilon times the square root of c. And square root of c is a constant. I want to prove that's continuous at c, so I just square root of c is a constant. So if I want to prove it's continuous at 4, I'm going to prove that I'm going to make delta equal to, if c is equal to 4, get 2 epsilon. If I want to prove that this is continuous at 7, I'm going to let delta equal square root of 7 times epsilon. So this is the basic idea behind the proof, and the key is just doing some high school algebra to get the x minus c in there. Why do you do the high school algebra? Because the only thing you can control is this delta statement here. So you want to get x minus c in there any way you can. If that involves multiplying by this crazy square root thing, then you do it. But then that gives me the x minus c, which makes me happy. Oh, and then I need to get rid of that x, which I can do just by estimating. I can get rid of the x at the cost of a less than or equal to, which is perfectly fine. So in the end, I'll get epsilon is bigger than that thing, which is bigger than or equal to that thing, which is bigger than or equal to this thing, which is exactly what I want. That's how the idea goes.